In this class, we're going to take a look at arithmetic sequences, which are sometimes referred to as arithmetic progressions. So when you first start sequences, it's usually an arithmetic sequence that you're actually looking at, but at that point we don't call it that. We don't have a name for it, it's just a sequence. And the thing that defines an arithmetic sequence is that each term is generated by a common difference to the previous term. In other words, you're adding or subtracting the same number every time, and that number has to be consistent. So we're adding 5, adding 5, adding 5, and that's going to carry on indefinitely. So that is the thing that defines an arithmetic progression or arithmetic sequence. In this case, we were adding 5 every time, but it's fine to subtract a number as well. You could think of it as adding a negative number, so you could say the common difference is a negative number, and you're adding that negative number, or just think of it as subtracting. So here, we're taking off 2 every time, so the common difference this time is minus 2, and that would just continue forever. It's not bounded by 0, you're allowed to pass through 0 and go more negative, and that would just carry on then into the negatives. What we want to do with arithmetic progressions, though, is to start to formalize them a little, and we want to start to think about what is a very common question with all sequences: how can we generate a particular term in the sequence without having to write them all out? If I wanted to know the 50th term here, do I have to write out 50 terms? Do I need to keep adding 5 every time? Or how can I get straight to that 50th term in a more efficient manner? And the way that we can do that is by generalizing what an arithmetic progression is. And sometimes we just think about these questions in general terms. So we don't always think about them with actual number examples. We just give them algebraic labels. So the way that we normally do this is we consider the first term to be a, okay, so just the first term, so that'll be equivalent to these ones here. And we know that every time that we generate a new number here, we're adding some common difference. So we're going to add some common difference, and we're going to call that common difference d. So the second term then would be a plus d, okay? Then we're going to add that common difference again, because we're always adding the same number every time. So we're just adding that d again, which is a plus d, which is a plus 2d. Okay, and then the next one would be a plus 3d, and that's just going to carry on indefinitely if we add another d every time. But remember that with these sequences, we're also interested in recognizing the placeholder number. In other words, oh, that's some very disturbing counting there, getting ahead of myself. 1, 2, let's try that again, 3, 4. So we're also interested in the placeholder number, which kind of links the term in the sequence with the actual placeholder. So how is 3 related to 1? How is 8 related to 2? So transferring that idea of placeholder over here, then this here is our first term, this is our second term, this is our third term, this is our fourth term. So you can quite quickly start to see a pattern in that these numbers that we're generating here, let me put a 1 in here for clarity, then these numbers we're generating here to get each term in this general sequence is 1 less than the placeholder number. So if we call the placeholder number n, as we normally call it, then that would tell us that a general formula for finding a term in an arithmetic sequence is to take your first term, because these have all got that first term in them. So take your first term, a, and a is going to be added to, or you're going to add to a, 1 off of this number. Now if this number is n, then it's 1 off of n, so it's n minus 1 times d. So that's the structure that we've recognized there. And that would give you the general term, which we might call a sub n. So for an arithmetic progression, an arithmetic sequence, a sub n equals a plus n minus 1 times d. And that's how we find each term. So if we did want to figure out the 50th term there, we would just plug in whatever that comes to be. So if we wanted to do, in that case, a sub 50, we would just plug in the first term, which is 3, and then we're going to add to that 50 minus 1 times d, which came to be, the d was 5 in that case. So it would be 3 plus 49 times 5. And then we'd work that out, and that would give us the answer. So what would that be? So if that was 50, then that would be 250, take away 5, so it's 245, so it's 248. So pretty quickly get that term, whereas if you wrote out all of those numbers to the 50th number, you're going to be there forever writing out all those numbers. So that's basically why we want to have the general formula. So if you're working with arithmetic progressions, which you probably will be, arithmetic sequences, if you're working a sequence topic, then it's good to remember that, and also to remember kind of how we got there, because that tells you basically why that formula works. The n-1 is basically because if you're considering 3 terms, then that means that you've got 2 gaps between the terms. So if the n value was 3, 1, 2, 3 terms, that means n-1 gaps between the terms. And it's the gaps that are giving you the plus d. So it's how many gaps you've got, this bit here, times d, 1d, 2d, so it's n-1 in that case. So just quickly applying that to this other example we've got down here. Let's say we wanted to work out let's say the 10th term in this sequence. So our a value here is 16, that's the first term. So a is 16. These guys are going down, taking off 2 each time. So that means that your d value, your common difference, is -2. And we're just going to take those and plug them into our formula. So let's say that we want to get that 10th term, which wouldn't be too bad this time, because you could just you could write out 10 fairly quickly. But we'll just do this for illustration. So a sub 10 would be a, which is 16, so the first term, plus if you're taking 10 terms, then you would need n-1, which is 10 minus 1, times the difference, which is -2. So just writing it like that, and we're going to get 16 plus, so this is going to become 10 minus 1, which is 9. I'll just quickly write that in actually. So that's going to become 9 times -2. So that becomes 16. 9 times -2 is -18. So minus 18. And then that comes out to be -2. And it wouldn't be that difficult to arrive at that. So that's 1, 2, 3, 4. So the 5th term would then be 8. The 6th term would then be 6. And then 4. And then 2. And then 0, and then -2. So that's term 4, 5, 6, 7, 8, 9, 10. So counting the terms out and writing them all out, like I just did there, and using the formula will give you the same answer. Going to the 10th position is not too bad. Going to the 50th would be a lot more time consuming. So the takeaway from this class really is that if you want to generate a sort of formula, I guess, for finding the terms in an arithmetic progression, you do it by counting the number of gaps in between the terms, and that's where the formula ends up. One thing to know about an arithmetic progression, because they're always getting bigger or smaller, so this one was getting bigger, this one was getting smaller, that means that by definition it cannot have a limit. So if you're familiar with the concept of a limit, then you know it means that the terms in the sequence approach a number. But this is not approaching any number, so we say that that one there diverges, and that one's diverging to positive infinity. This one diverges and tends towards negative infinity. That means that in general, an arithmetic progression, I mean, almost by definition, has no limit. So they're always divergent. They always diverge because they're always getting bigger every time or smaller every time. So that's another key thing to know about an arithmetic progression. If you're working with this topic at the moment, it might be worth spending a little time getting to grips with this formula, just using it a few times to get comfortable with how it works and just seeing how arithmetic progressions work. It's always good to write out a few terms just to start to get a feel for them and to see the direction that they're going in. But in terms of sequences, arithmetic progressions are probably the easiest, so it's definitely like the starting point. So spend a little time working a few practice questions on this topic.